Okay, so off we go. Last time we had just finished up talking about determinant, and recall that there's this big theorem here. You may have seen a version of this theorem in your linear algebra class, but I like to represent and make sure everyone's seen this version of it. Anyway, moving along, so we're going to start talking about cross products now. Again, I think you've probably seen this in some form or another in linear algebra class. I want to remind you that there are different ways to approach all of the stuff that's in this section of the book. So my approach, in which I think this approach is the best for sort of geometric intuition and that kind of thing. And the book's approach has some very nice rigor advantages that I just don't think are really what we need to focus on in this course. Anyway, okay, so I'm starting with a definition. First cat out of the bag, I have to point out this is a different definition than the book gives. It's equivalent, means exactly the same thing, but it is a different version, you might say, of the definition. So I'm going to define the cross product to be this right here. So just a formula. It's a vector whose coordinates are given by these expressions. Okay. Why on earth would we be interested in such a thing? A very reasonable question, and we're going to be developing that over the next few minutes here. Okay, first thing you're going to notice is that each one of these coordinates is itself a little 2x2 determinant. Not hard to notice. You may then further notice that the whole thing is actually a kind of a sort of a 3x3 determinant asterisk. Technically, this isn't really quite a determinant because a determinant is something you do to a matrix. And this isn't really quite exactly a matrix because look at the top row. The elements in this top row, they're not even numbers. They're vectors. You're not really supposed to, can you do that? Right? I mean, this seems a little fishy. So I'm going to call this a symbolic matrix, just to avoid any potential trouble there. And then likewise, we're going to take the symbolic determinant. We're going to go through and apply the regular cofactor expansion formula for determinant as if that should apply here. And then just whatever it is what it is. So that's the symbolic determinant. And if you do that, what you'll find is that it is exactly equal to the cross product. So how about that? Now, the advantage, why would we want to sully our definition here with questionable nonsense about symbolic matrices and symbolic determinants? And the reason why is this expression on the right is super easy to remember. Right? It's very, very convenient. Standard basis vectors on the top row, then the first vector for the next row, then the second vector for the third row. Super easy. Whereas these formulas here, I think it's almost a given that you're going to misremember it at some point. You're going to get these two terms backwards, or you're going to forget this minus sign or something. Right? Very easy to oops that formula. Okay, so for whatever it's worth, in my life, I've never memorized this formula. Haven't needed it. I couldn't help but memorize that one. Okay. Yeah?
Wait, sorry, what do you mean by symbolic determinant?
Yeah, so you remember the cofactor expansion for determinants, right?
Yeah.
Okay, so in other words, as you sort of just go along the top row, and for example, you're going to take this and multiply the determinant of this submatrix, right? So just do that, except instead of this being a number that you're multiplying by that determinant number, it's going to be this vector that you're multiplying by this submatrix determinant number, etc. Yeah. All right. Okay, so neat fact, if you take this formula for the cross product, there it is, and if you just dot it with an arbitrary third vector called C, what you will quickly notice is that the process of going through this dot product is literally exactly the same as the process of computing this third formula over here on the right. So namely, C1 times A2B3 minus A3B2, right? Well, that's exactly what you would get if you were doing the cofactor expansion, and there's C1, that element, and this is the determinant of that. It's just exactly the same thing. So conveniently, we get yet another formula of interest, and that is this right here, that expression is equal to that expression. So this is called a triple product because there's three vectors that go into this expression called a triple product. And conveniently, interestingly, triple products are determinants. Okay. Very important formula. The reason this formula is important is because we already know cool geometric information about determinants, and we already know cool geometric information about dot products. And so having this formula is going to help us understand geometric features of the cross product. Okay, so this is a kind of a foot in the door for a lot of things. Yes?
So are those, I'm just curious, are those orders like reversible?
That's a great question. So this is a dot product, and of course dot product is commutative, right? That said, when you're looking at this formula here, switching them is effectively moving a row around, and we get a little scared when you move rows around. Wait a minute, is there a minus sign in there? Oh gosh, something to worry about there, right? Not that you can't deal with that, of course, but for that reason, just to avoid the potential confusion, I have a personal policy, and you're not required to follow this, but I do recommend it. I think you'll find this useful. I always write a triple product with the dot product on the left and the cross product on the right. I think you'll find that that's, in the long run, just very helpful. It avoids confusion. I've seen student test papers where they're a little fast and loose with this, and inadvertently they can write down something that kind of looks like it ought to be true, but isn't. It's sometimes not even not true, but it is not clear. And so, yeah, I advise always writing it down like that. Okay. Right. Okay, so now here begins a long list of properties that we're going to see for cross products. I've already mentioned that, sadly, at least sadly for me, we don't have time to go through all of the proofs of the properties that we're going to talk about here. So when I say we're not going to go through it, I mean you're not responsible for the proofs in this section. Now that said, even though you're not responsible for it, I do think there are some really useful ideas. If you look at this proof here, for example, this idea that a cross product is always orthogonal to both of the input vectors, you can take an algebraic point of view on this. You can just compute these dot products and plug and chug and crank out the algebra, and that establishes with complete rigor that the fact is true, but it also leaves you with no intuition about why it's true. Right? So I think there's good intuition to be had in these arguments. So I've left these in the notes in case you want to look through them. Again, I think it's a nice opportunity. I encourage you to think it through. But again, you don't have to. You're not responsible for it. Just the results that we're about to go through here. So let me just, as a formality, I'm going to go ahead and cross that off because you're not responsible for it. But you are, of course, responsible for the result, for the final theorem. Okay, so again, neat fact, I think you probably already know this one, but cross products are always orthogonal to both of the input vectors. Argument for your consideration. Let's see here. Here's another one. This one's weird looking. These triple products are all equal. Now, again, there's an argument here. It's actually a fairly heavily geometric argument, which again always gives me personally nice satisfaction and intuition. So take a look, please. That said, I do want to point out that this result here, that these three triple products are equal, at a quick glance, it might kind of look like, oh, that's just like a commutativity or something. Isn't that like associativity maybe? I guess it looks a lot more like an associativity. It seems like it's a perfectly expected result. But let me point out, it's really, really not. In fact, it's really, really surprising. So, for example, this expression on the left, the b, is part of the cross product. In this other expression that it's equal to, the b is not part of the cross product. So this isn't like some little simple commutativity or just kind of moving parentheses around. Something very different is happening in this second expression compared to this first expression. Right? So this is a real eyebrow raiser. Should strike you as surprising that this is true, at least at first glance. And then, again, if you want that intuitive satisfaction of not just why is it true, but why should it be true, take a look at this argument here. Okay, all right, moving along. Another neat theorem here. The magnitude of the cross product tells you something interesting. All right, we've already seen that the direction of the cross product is interesting. It's in a direction that's orthogonal to both of the input directions. But the magnitude also interesting. The magnitude of the cross product tells you, let's see if I can get this to, okay, here we go. The magnitude of the cross product tells you about the area of a certain parallelogram. This is a notation that I like for indicating a parallelogram. You'll notice the two little parallel lines. That's to be suggestive of parallel something, right? And this is a parallelogram because if you look at what follows, there are two vectors there, A and B, right? So this notation here represents this parallelogram like that. It's the parallelogram defined by those two vectors. So, weird fact that the area of the parallelogram is equal to the magnitude of the cross product. Really surprising result. Again, cool argument. I hope you'll take a look. Not responsible for it. You don't have to, but I think there's some nice intuition to be had there. There's also, it's a nice example of a really interesting proof technique that comes up in a lot of other places. It's what I like to call the mathematical bank shot, as a reference to billiards. When you bounce the ball off the rail and it goes over somewhere else. So the idea is, here are the two things that we're interested in. And normally, if you want to prove that two things are equal, what you do is you compute one and show that it's equal to the other, or you compute the other and show it's equal to the one. I mean, typically, we do that a lot, right? The way that you prove this result is to introduce a third item that we're actually not interested in at all, seemingly going in a direction that has no relevance to what we're actually caring about, and then showing that this relates to each of the two things that we're interested in. So we show that these two green expressions are equal by looking at this blue expression and relating it to each of them. I think it's a very cool style of an argument. And again, you're not responsible. You don't have to look at this, but I do encourage it. Okay, so neat result. Make sure you know this result. Okay, here's another couple of them. Cross product has a feature that's vaguely reminiscent of a feature of dot products. So you may recall we have an old theorem, way old theorem, that if the dot product is 0, then that means that the two vectors are, I'm going to say, perpendicular, but you know what I mean. There's got to worry about the zeros and stuff, but it's perpendicular or something anomalous. Loosely speaking, dot product equals 0 means perpendicular. Likewise, loosely speaking, cross product being 0 means that they're parallel. And again, technically, this doesn't really quite mean that they're parallel. There's what if one's 0, what if the other's 0, stuff like that, right? But what they are always is linearly dependent. And remember the kind of the generic, most of the time when you have a pair of vectors that are dependent, they're parallel. Most of the time. Except for annoying 0 type cases. So yeah, I think that's, again, highly analogous to dot product. Vanishing dot product means perpendicular. Vanishing cross product means parallel. Nice. Okay, next. This list right here. A, comma, B, comma, cross product. Again, loosely speaking, just because this is the following is how people tend to think about this. This list is in right-hand order. I have to correct myself again. It's technically not always right-hand order because it could be 0, that could be 0, the cross product could be 0, various things could be 0, in which case it's neither right nor left. So when I say it's always in right-hand order, okay, yeah, technically no, right? But what it is it's never left-hand order. And so generically, it's right-hand order. Everybody okay with that? Yeah.
What exactly does the notation mean, A, comma, B, comma?
This is a list. So remember we talked about if you have if you want to talk about a list of 3 things, then that list, so where 1 is first, 1 second, it's all that business with right hand, left hand. Yeah. Right. Okay. Okay, so what this gives you is a nice, again, little bit of geometric intuition for what I'm going to call the right-hand rule, kind of. You may have heard of the right-hand rule. There's actually several different versions of the right-hand rule, depending on context. But the idea here is if you have 2 vectors that you want to cross, put your index finger in the direction of A, put your middle finger in the direction of B, the usual rules about what to do with your index and middle fingers and what's got to be parallel and no hand yoga and all that stuff, right? First vector, second vector, your thumb will point in the direction of the cross product. So that helps you keep it straight. Wait, does it go up or down or to the left or to the... Oh, sorry, I didn't mean to flip anybody off there. Which direction of the 2 possibilities perpendicular to the 2 input vectors? Should it be that way or should it be that way? Your right hand, and using the right hand rule will keep that straight for you. Okay. So again, cool proof. Take a look. You don't have to. You're not responsible, but I think it's nice and worth your time. Okay. Yeah. So I've already spent some time talking about how there are different ways to sort of traveling salesman problem move through all of the points that we need to hit on this topic. This is what I'm going to call a geometric description of the cross product. The cross product is always the unique vector that satisfies these 3 rules. The textbook, and not just our textbook, right, but many books, go through all of this in a totally different order. Our textbook, in fact, makes this the definition. You'll notice in the textbook, in this section, when they say cross product the very first time, definition, they define the cross product as the unique vector that satisfies these 3 properties. And then from these geometric properties, it then derives all the other properties and the formula that we started with. Right? So it's a different way to kind of go through things. And again, pros and cons. I like my way better because I think it's better for geometric intuition. The book likes this way better, and it does have some nice advantages. I think the book's got me on rigor, for example. But that's not what this course is really about quite, right? So that's just not, we don't need to worry about that. And the book has the disadvantage, and I think you'll notice this, if you look at the book's presentation, there's a lot of nasty algebra and tedious computation that is what I call opaque. I find it very unsatisfying, and it doesn't give me the satisfaction. It doesn't make it. I don't feel like I walk away understanding, oh, that's why that ought to be true. It's just rigorously true, but no why. So, again, pros and cons. Okay. So let's see here. A few more things. These two vectors are negatives of each other. This is worth pointing out for a couple of reasons. On the one hand, a lot of students play a little bit too fast and loose with multiplication signs, right? Because you've been trained since you were, I don't know, when do they introduce multiplication in elementary school? Like second grade or something? So since second grade or so, you've been trained to think, oh yeah, when you multiply, you can switch the order that it's in. Very importantly, you can't with cross products. Cross products are not commutative. So do be careful about that. However, notice this is saying that there is something to be said. There is an equal sign in here. And what cross product is anti-commutative. When you switch the order of vectors in a cross product, that introduces a minus sign. And by the way, a pretty good hand-waving satisfaction on this is, remember the right-hand rule, right? First vector, second vector, thumb points in the direction of the cross product. If I switch the order of these two vectors, now again, I have to maintain this same hand gesture, but I want to point my index finger where my middle finger is. I want to point my middle finger where my index finger is. And notice, in order to do that, I have to flip my hand literally upside down. Right? So, nice little bit of intuitive geometric satisfaction, independent of the algebra. Now, of course, you can prove this result with the algebra. Write it out, crank it out. And the algebra never lies. That doesn't mean it's helpful, right? It's for intuition purposes, not particularly good. Okay. Pausing. How are we doing? Everybody all right? Okay, couple of other things here. Let's see here. Linearity. Let's talk about that. You've heard me talk about linearity last week, I guess it was. And specifically, I claimed that this is linear, that this function, a cross x, is linear. In fact, there was a homework exercise, you may recall, to show that this function is linear. So let me expand out what linearity means for this function. Linearity means, as we've discussed before, that a linear combination on the inside corresponds with a linear combination on the outside, right? And that you get the same thing either way. That's what linearity means. Notice how the function is appearing here. T is represented by a crossing with whatever. And so there's T, and there's T, and there's T. So you can kind of walk your way through this equation, and it pretty literally says T of a linear combination is that linear combination of T of the two original things, just like in the definition. Okay, now how are you going to prove this? You're going to prove this by using properties of cross product that I hope and assume that you saw back in linear algebra. Namely, we already know that cross product is distributive, and we already know that cross product is scalar associative. And so you just use those properties of cross product and take this expression on the left, and in 2 or 3 steps turn it into the expression on the right. Okay. All right, so you don't have to break it down to coordinates. Okay. Now notice here I put a cross on the left. By contrast, you could put it on the right. Now here the order does matter, right? A cross X is not the same thing as X cross A. Still though, still linear. There's T, and notice again the linearity comes in because here I have a linear combination on the inside, and here I have the linear combination on the outside. So same basic idea, just sort of things are turned around a bit. Yeah, was that? Yeah. Go ahead.
So if those were like the same x and a vectors,
Yeah.
would the resulting like linear combination be the negative of?
Yep. So this function and this function are negatives of each other. Yeah, absolutely. Is that what you were asking?
Yeah.
Yes. Yeah.
I have the
Oh, it's the exact same question. Okay, what are the odds? All right. Cool. Last, just a quick warning. And I've said this before, but we've all been trained since we were yay high to whenever you see times with certain key properties that you just, you don't even notice yourself doing it sometimes, right? Because you've been doing it for so long. So, for example, when you're multiplying, move parentheses around all you like, it's all good. Again, not so for cross products. And it's confusing because in terms of the notation, we use the same symbol here that we used in elementary school for an operation that is associative. That's unfortunate, right? The notation there is kind of tragic. Anyway, very importantly, not associative. And it's not anti-associative either. It's just not. So nothing. There's no sort of silver lining on this one. All right. Okay. Let's see here. There we go. Okay, a couple of quick applications. I'm going to be real quick with the applications because this isn't a physics class, and most of my incentive here is just to persuade you that the cross product isn't just purely a made-up, abstract, mathematical, figment of somebody's imagination, but this actually does have some bearing on the real world. So let's talk about torque, for example. And if you have something turning on an axis, so here's an axis, maybe you've got a screw that you've screwed into a board, for example, right? The way you get that screw into the board, well, you don't grab the screw by the head of the screw with your fingers, right? That's, unless you have really strong fingers, because it's just really hard to turn. No, you get a wrench, right? And the wrench might have a nice sort of width to it, and that makes the turning so much easier. You can turn so much harder by applying, for example, a force kind of like this, maybe, as you tighten or untighten, I guess in this case, that screw. So this is the idea of torque. So torque is kind of like force in a way. Force says how hard are you pushing something. Torque says how hard are you twisting something, right? And you can see it's going to depend, of course, on what this r vector is, and it's going to depend on what the f vector is, and specifically the actual torque. How hard are we turning that screw is computed with a cross product. So this isn't some mathematician imposing their preference on the physical world. It's not at all, right? This is the way the physical world works. It was like that when we got here, right? This is intrinsic to reality. So therefore, cross product, you can see naturally and unavoidably is part of how the physical world works. Here's another example. Magnetic fields. So this is a weird fact, by the way, but if you have a charged particle that is moving, and it's moving through a magnetic field, let's say the magnetic field is over here like this. So charged particle moving that way, magnetic field pointing in the direction of my middle finger here that way. And again, don't ask me why. I didn't do this. Mathematicians didn't impose this. The world was like this when we got here. But it turns out that in this scenario, there is a force applied to the charged particle. Very counterintuitive. It's unexpected. But this is, again, this is how it was. This is very empirical. And the force is that way, and the force is a cross product of the movement of the charged particle and the magnetic field that it's moving through. Very surprising fact. And again, unavoidably, naturally part of the world as it is. So the cross product, unavoidably natural. Is that cool? Any questions? Pausing? Everybody's happy? Yeah.
I'm just trying to understand what this torque vector is referring to exactly. So, like,
Yeah.
in the drawing that's on the screen, the torque vector it has to be perpendicular to R and F. So it's almost like it's coming out.
That's right. Pretty much. I mean, technically, as we have it drawn here, if the force were to have, let's say, an inward component, then the torque vector wouldn't be parallel to this purple line anymore, right? But the component in the direction of the purple line is what would tell you how hard you're twisting the screw, right? And everything else is kind of sort of irrelevant to what's actually happening. Yeah. Does that make sense?
Yeah.
Okay. Yeah. Right. Okay. Cool. Yes.
How does cycling affect the two vectors?
How does what now?
Like when you cycle around the order of.
Oh, the order in the cross product. Yeah, that's this one right here. That if you switch the order of the vectors, so if you put A where B was and B where A was, then you get the negative of the otherwise. Yeah. Is that what you were asking?
No,
No?
in the list of how we're doing the A, B, and A, cross B is not left-handed.
Oh yeah, this one right here.
Yeah.
Okay.
What happens if we cycle?
Oh yeah, so when you cycle a list, right, that doesn't affect right hand versus left hand. So you're right that this could be rephrased. I could rephrase this property as cross product, comma A, comma B, and that was also never left hand order, usually right hand order. Yeah. There's three different ways to state this that are all morally the same statement. I state it this way because I like to think of the inputs causing the output, and so it just feels like this ought to be last. But yeah, you're right. There are other ways to say morally the same thing. Yeah.
So cycling the list is like.
I'm sorry, I can't hear you.
Cycling the list is like the equivalent of rotating the whole system.
Say it one more time. I'm sorry.
Cycling the list is doing the same thing as if you rotated the whole system.
As if you rotate the system? Well, yeah, kind of. I mean, so this is the hand gesture that I was doing right last time. So cycling corresponds to, what was third is now second. Depending on how. Anyway, you know what I mean. This is literally the geometric version of what happens when you cycle through a list. Right? So, yeah, it kind of is a rotation. It looks sort of like a rotation. Technically, it doesn't have to be a rotation, though. Because, for example, see here, let me dramatically make these two not perpendicular to each other. If I cycle this list, can I do this with my, I don't know if I have okay, yeah, there we go. So this cycles to that. It's not really quite a rotation. Exactly. But it's vaguely reminiscent of a rotation. Is that satisfying? Yeah. Okay. All right. Okay, so we are done with 1.4 now. Moving on to 1.5. This is another one of these sections where I'm going to go pretty quickly through it because I think you've seen a lot of this before. You've probably seen some of it anyway. And, tough choices and all that. When we get to the Chapter 7 material about divergence and curl and these kinds of things, you'll see why I feel the need to move quickly through this stuff. So let's establish what the equation for a plane is. And if you come to me with a point in a plane and a vector perpendicular to the plane, I claim that this characterizes a plane, right? Given this point, given that vector, there will always be exactly one plane that goes through the point and is perpendicular to that non-zero normal vector. So given that geometric description, how would we write down the equation? And keep in mind the purpose of an equation is to be a test. So I need to be able to write something down here that tests a given point. So let's say this point here. If I want to decide, is that point X on this plane as defined up here? How would I test that point? And my proposal is this, that I test whether that point is in the plane by looking at this difference vector x minus x naught and asking if that difference vector is parallel to the plane. Now this is just a geometric appeal, but we're given that x naught's in the plane. That's given. So if x is in the plane also, then I'm looking at a vector that has tail and head in the plane, and that means that that difference is parallel to the plane. Okay. Then I make the observation that parallel to the plane, let me just erase this stuff there. Parallel to the plane would mean perpendicular to the normal vector. That makes sense to everybody? If this orange vector is parallel to the plane, then it's perpendicular to the vector perpendicular to the plane. Yeah?
X naught is just a point?
Correct. Yeah. Yep. And X is a point that I'm testing to see if it's in the plane. Yeah.
I'm confused why you put the vector notation over X.
Do what now?
You put like the vector notation over X naught.
Yes, right. So now, that's another fact about vectors that I'm sort of referring back to from linear algebra. So there's a one-to-one correspondence between points and vectors by what we call the position vector for a point. Right. So if you give me a point, I can talk about the arrow whose tail is at the origin and whose head is at that point. So for any point, there's a corresponding vector, and for any vector, there's a corresponding point. So what's convenient about conflating those is that it saves me having to write down twice as many formulas. Right? So like we have a formula for vector plus vector. Why don't we have a formula for point plus vector? Point plus vector is very geometrically natural. Why don't we have a formula for it? Well, because it's the exact same formula. Right? And it's just, with that in mind, it's just easy to, it's very convenient to conflate these with the understanding that it's the listeners, it's the viewers' sort of perpetual obligation to always think through exactly what do we mean by whatever we write down. So here, for example, this x naught, I've drawn a point. So, yeah, so I'm referring to the location. But algebraically, I can treat it like an arrow with its tail at the origin because, well, why not? Okay. Alrighty. So, yeah. So how do we write down perpendicularity? Well, dot product is equal to 0. Now, by the way, I did just commit a little math crime. Micro math crime. I said perpendicular here, but then I wrote orthogonal. Right? Now that brings up the question, wait a minute, which is right? Do I want to allow for the possibility that x minus x naught might be 0? Let's just think it through. What happens if x minus x naught is the 0 vector? Okay, well, if x minus x naught is the 0 vector, that means x is equal to x naught. X naught definitely is in the plane. Right? It for sure is. It's given to be in the plane. So when I say orthogonal, perpendicular, I better make the choice that allows for the possibility that this difference might be 0. Because it kind of has to. So that's why orthogonal is actually what we're interested in here, not perpendicular. A little subtlety to think about there. Okay, so a little bit of algebra. I can rewrite this like that. This is my slightly preferred version of that equation, and then of course you can take this equation and we've got this normal vector. It's going to have certain coordinates, let's call them A, B, and C, and having done so, then this rewrites like that. Don't forget that n and x naught are both given, so that dot product is some number. And lo and behold, then, our equation for a plane can be rewritten like that. Now, these two equations have, again, pros and cons. This one at the bottom, the ax plus by, all this business, is familiar looking. Right? Kind of reminds us of the equation of a line. It's just scalars. For function arithmetic, no fancy dot products involved, right? And that's arguably a good thing, but it's also arguably a bad thing. I kind of like this version better myself because, again, I can see important ideas. I can see the role that x naught plays in this equation. I can't see it in this equation. I can see that there's a dot product involved. It's easier to connect back to geometrically the point. Right? Geometrically the point being that this difference and that normal vector need to be orthogonal. This is really a better formula from an ideas standpoint. Right? Nevertheless, both true. So make sure to know both. And now let me make another pitch here. One nice thing about this expression, or this formula, the equation of a line, is that just looking at the coefficients, I can immediately conclude my normal vector. Right, you just eyeball glance. I don't even have to do any work there. Just, okay, what are my coefficients? A, B, C? Okay, there's my normal vector. Pretty great, yeah.
So would x, y, and z in that equation represent the difference in points between x and x naught?
Great question. No. So all the x naught business I've already moved over to here, right? I'm hitting the wrong button. That's where I'm going the wrong way. Here we go. So the x minus x naught thing, I've already kind of separated that out. So this is representing just x, y, and z is representing just the x vector. That's the point you're testing to see if it's on the plane. Yeah.
And if it was on the plane, would that be 0? Would D equal 0?
Nope. So that's you got to be careful not to conflate these two equations, right? So if you're talking about n dot x on the left, then the right is n dot x naught, right? It's only if you're looking at difference dot normal on the left that you get 0 on the right. Yeah. Okay. All right, let's see an example of this in action. We are given 3 points. Like so. And we want to find the equation of the plane. Here's the plane. Oh, I didn't do that right, did I? Here, find the equation of the plane. Given those 3 points, I'm going to point out that there's a million questions that all kind of have this same kind of general structure, which is, hey, here's some information about some geometric objects. Here's a related geometric object. How would we understand the related geometric object? So here we're given information about points, geometric objects, and we want to find information, namely an equation, for the plane containing them. That's a related geometric object. Okay. So there are, as it turns out, while there are millions of versions of these kinds of questions, there's a few little clever tricks that people have noticed and that are really important to know, right? So, if you're playing tic-tac-toe with somebody, there's certain tricks that you'd always start with the center square and, you know, things like that. You've been around the block enough times, you just know certain tricks. So what I'm about to show you here is one of these very, very important tricks. And the big trick here, for which I thank my mathematical predecessors, is to subtract one of the points from the other two, like this, and observe that that means that these two vectors, b minus a and c minus a, have to be parallel to the plane, and therefore that their cross product must be perpendicular to the plane. Neat trick, right? I wish I had thought of this originally, but somebody showed me. Find vectors parallel to the plane. Crossing gives you something perpendicular to the plane. So you're going to use that lots and lots and lots as you're doing exercises for this section. And in this case, that's kind of all we needed, because after all, let's see here, all we need to find the equation of a plane is a normal vector. And, oh, well, let's see, I guess we also need a point in the plane. Good news, we've got 3 of them. Take your pick, doesn't matter. You know, I guess I kind of like A best because of the numbers are smaller, right? It doesn't matter. Take any of these 3 points that you like. All good. Okay, a couple of neat facts I want to walk us through. Turns out that when you have an equation for a plane, and if there are no y's in the equation, right, so ax plus by plus cz, yeah, but no y, so ax plus 0 y plus cz equals d. This alone, and by the way, so easily observed. Look, I see a 0. Poof, observed, right? So super easy to notice when this happens. There's no y's in the equation. You get a powerful geometric conclusion, and that is that the plane is parallel to the y-axis. So easy algebraic observation gives you useful geometric punchline. So pretty sweet deal. A pretty good thing to be aware of. Let me walk you through the arguments. Not much to it, really. We've already observed that when you have an equation, the coefficients tell you the normal vector. So I know my normal vector is A0C. I can very easily observe that dot product with the E2 is 0, and so therefore this is perpendicular to the y-axis. And now a geometric appeal, if my normal vector is perpendicular to the y-axis, that means the plane must be parallel to the y-axis. So, as desired. Yeah?
I don't really understand D.
You don't understand what?
D.
I'm sorry, I'm not hearing you.
D. Like
Oh, D. Oh, yeah. So D is just whatever the right-hand side ends up being. So keep in mind that, here's our general equation. I mean, this is just how I like to write it. And n is given and x naught is given, right? And so the point is, this is just some number, and I'm just going to call it D. So yeah, we don't. I mean, D isn't really in the picture exactly. It's just whatever you get when you dot those vectors. Yeah, in the back. Yeah, sure. So the y-axis is characterized, for example, by the vector E2. Oh, let me do this in pencil. The vector E2, right? And E2 has coordinates 0, 1, 0. And it's just pretty easy to see the algebra that this dot that is always going to be 0. Does that make sense? Yeah. Right. Yep.
So if D, D is
Uh-huh.
We know the coordinates of n are a, b, c. Can we also use that to like set d equal to the vector a, b, c dot an arbitrary vector and then like the coordinates of that arbitrary vector to find the common component?
I guess I'm not quite following. It sounds like you're proposing an alternative approach. Is that right?
I guess I'm trying to, like, I see how we can get from the vector form of the equation to the ax plus by plus z equals z form of the equation.
Yeah.
I'm just trying to figure out how we would work backwards to get
I understand. So you're trying to figure out how would you. Okay, now my computer is misbehaving. Sorry about that. Here I am. Okay, so I wanted to go back one page. So you're asking how can I use D to sort of reverse engineer and figure out what x naught is. Is that right? Yeah, well, you can't solve for x naught because there's actually a bunch of different points that are in the plane. So you don't need to solve. You can just kind of manufacture one. So just pick the first two coordinates to be 0, let's say, and then the third coordinate's got to be whatever it's got to be to make the numbers work out. Yeah. You can, but the point is you don't even typically need, if you already know D, then, I suppose sometimes you need to find a point, but it's really not a solving thing. Yeah. Okay, so we are actually out of time now. We will pick up here next time, and hope you all have a good weekend. See you later. Okay, let's see.